Okay, so what I wanted to talk about today was some of the test benches, and I've come up with part of a presentation. It does is I've only got slides up to 16. By the time I'm done, there will be slides up to at least 50. I just haven't finished it yet. Uh, the yesterday I did do just a Google search on um, I forget how I wrote it. Something like writing there it is, VHL test bench in a tutorial. And I think it was this one. I could be wrong, but I know it was a PDF file. And it was pretty good what I got to see out of it. So what I'm getting at here is uh, don't always wait for me to come up with something here. Uh, Go ahead and do some searches for it. I don't know what's happening to the rest of this. It's now it's not coming up with it. Okay, 1 of 17. And I'm just going to show you this one real quick. Uh, it's taken a while to come in. Yeah, this looks like the right one. It's taken a few seconds. I'll come back to that. Okay, let's get started with the presentation. And so this is what I hope to talk about. What's usually going to be done here is I'm going to finish it. I'm not done today. I hope I have it finished by Thursday. Uh, I decided to go with this particular uh, state machine design just because it was kind of different, and I didn't want to figure it all out with uh, as a hardware circuit, so I just wanted to do VHDL. So here's that one that I said was help for project 4, and so let's look at, we got states 1, 2, 3, 4, and 5, or we could call them A, B, C, D, E. We got 2 inputs, R and S, and 1 output, Z. So this has got a lot of good stuff in it that would be good to have on a test bench. So here's the state table that I came up with, and if you're wondering where all this stuff is, I've put it on, let's go back out over here to Moodle, and I've put it on all the on both uh, my digital systems classes. And it says up here, example. Uh, I'm not sure how great an example it is, but this is the same diagram. This is the same state table. And it's fairly easy to go back and forth between these two and say, okay, if I'm in state 1 or state A, and I've decided that my state variables are going to be 0, 0, 0, 1. The only thing that made this one real similar to the to project 4 was that it was one hot encoding. So I can find that on here. Here's state 1 or state A. If uh, if I call it state 1, if R is 0 or if R is 1, well, those are the only 2 transitions leaving this state, and it'll either go to C or B, which is states 2 or 3. So looking back at this, if R is a 1, I go to state 2 or B. If R is a 0, I go to state 3 or C. And that's what I've got showing here. Now the great thing about this is if you're not going to do a hardware design, if you're just going to do a VHDL design, then you don't need to look at these columns at all. We let Xilinx come up with uh, what kind of flip-flops it wants to use. We do need Z. We do need the output line. Okay. Uh, so here's both the diagram and let me do this. Here's both the diagram and the table. And I've gotten rid of the flip-flop columns. So the next thing I have, if I'm going to implement this, I have to really take a look at this. So I've at least got to come up with this much of a state machine before I start trying to design it. Now, one thing I don't see in this or in this is a reset. Well, we almost always have to have a reset unless uh, unless you've got every possible state in your state variables. If you don't, then you have a good chance of, when you turn it on, of going to that state that you don't have anything defined for, and your system won't work. So I've gotten used to putting a reset signal in there. So that's one thing. The other thing here is these never show a clock, but we need a clock. So we have to include that. Now, this one's been a topic of discussion. Do we need to name it clock, or do we need to name it CLK? You could name it something else. You could name it ZZ or something like that, something that you know Xilinx won't pick up as a clock, because it's been my experience that if you had a combinational circuit and you didn't need a clock, Xilinx would put one in the test bench. But if you needed a clock, and so there was a signal out there named something that could be interpreted as clock, it wouldn't put one in there for you. So I would always someplace have a copy, and it'll be in this presentation when I'm done with it. I would always have someplace with a copy of what does a what are the lines that need to be input in there to make sure that a clock works. Okay, so here's the beginning of my state machine. I've got it, I'm calling it attempt 1. I've got R and S as inputs. My only output is Z. I've created a new signal that's not showing up on here called reset. I've got a clock called CLK, and since it's one hot encoding, I've got five state variables, or five flip-flops that are going to be there. So I have Q is output standard logic vector 4 down to 0. Now, one hot encoding is not normal. It's just I decided on project 4 to do it that way. It's just a way that it can be done. It's not everything's out there that's one hot encoding. Okay, so the next one was the rest of this state machine. And again, I looked over here. Well, the first thing I did was say, well, I'm going to create a signal called QX. And I do this all the time because, like in things like this, I cannot have this signal Q, but it's one of the outputs of my state machine here. So here's Q. I can see the output, but I cannot have Q on both sides of this assignment statement. Xilinx will get all upset about it. So the best thing to do then is to create a signal that is basically equivalent to that, and make it a standard logic vector. Same thing, 4 down to 0. And then this is the one I work with. The signal is the one I work with during the process. And at the end of the process, I assign whatever I've come up with QX to be, I assign it to Q, and it keeps from having any errors. Z is my output, and so the next thing I have to do is I've got these states A, B, C, D, or E. So I almost always create a new type of variable called a state type, and it can take on the values of A, B, C, D, or E, and that's it. And then if I do that, that's just creating a new type of variable, and I don't have a variable like that yet. So I created a new signal and called it X and said that it was going to be of type state type. Okay. And so X is allowing me to now work with my states. So I can say if I'm in state A or state B or 2 or E or D or whatever. Okay. The next set right here, what I'm doing is using my reset. I tried to do this and this gave me a bunch of errors. So that's why I've got my Z down here at the bottom. But if reset equals 0, so I was using an asynchronous active low reset, and if it was 0, then I would say that my state is A. I would go here, and that my state variables would be 0, 0, 0, 0, 1, or Q. The outputs flip-flops would say that. So my least significant flip-flop would be a 1, and the rest of them would be zeros. Okay, now I know that puts me with Z as being a 0. I can see that right down here. But I'll have to wait till I come down here, and when I get through with this whole process, which will, this process will end right here. I'll come down here. I can't move this, but it says end process. Then the next line will be that Z is assigned to 1 when my state is either X or I'm sorry, E or D, else it's assigned to 0. So if I'm in state A, I won't be in E or D, so it'll be assigned to 0. And then this QX will be assigned to Q, and my output will actually be 0, 0, 0, 0, 1. Okay, so the next part of my process is an active low clock, and I know this is kind of messy, but I decided to put it in there. And I'm going to use the case statement to use the state variable. So if I'm in state A, then this is what I'm going to do. If I'm in state B, this is what I'm going to do at C and D or E. And then it also lets me look at the variables R and S. So here in this first one, since I know I'm going to be in A, because this is my first time into this, it's going to say, these are the values of the flip-flops. If R is equal to 0, well, I can read that right off this diagram. That's why I've pointed over to this. I can read it right off this diagram. I don't need even this table. The diagram tells me if R equals 0, then my next state is going to be C, and my state variable or my flip-flops value Q's are going to be 0, 0, 1, 0, 0. And that'll get assigned at the end of this process. Now the table also shows it, so I don't need both of these, the diagram and the table. I just need one. So here it says if R is a 0, my next state's going to be C, and here's the values of my flip-flops. and my output's going to be a 0. Well, all that says that here and down here at the end of the process. So here, since I'm in, if R is equal to 0, then I'm going to go to state C. Z says it's a 1 if I'm in E or D, but I'm not, so it'll be a 0, just like it should be. And here's my value for Q, and so that's going to be the value for Q down there. If R is a 1, looking at this table again, if R is a 1, I'm showing this green arrow that comes over and points here. So if I'm in state A and R is a 1, I'll move to state B. Okay, my output will be a 0, and I can put all that in here just by looking at the diagram. So I say if state A, then if R equals 0, or I'm sorry, R equals 1, then I go from A to B. The output's going to be 0, and my state value, I might need to have this in order to come up with that state value, but it's 0, 0, 0, 1, 0. Okay, so now here X is assigned to B, so I know that I'm in state B. That really doesn't matter. This is what's important when I come out to my actual circuit. 0, 0, 0, 1, 0, and that's going to be assigned to Q. And then I look at Z and say that I'm in state B, so it's neither one of these, so that Z will be assigned to 0, and that's showing right there. Okay, the rest of them are all the same thing. When X is equal to B, in other words, I'm in state 2. Well, look what comes out of state 2. I've got this line, S is equal to 1, and then I've got this one where S equals 0 and R equals 0, and this one where S equals 0 and R equals 1. So I've got 3 transitions coming out of state B, and I better have 3 here. Only one way to get into state B. So here it shows that if R and S are both 0, then X is going to be in state E, which is down here, state 5, and Z is going to be a 1. And that all takes place in here. Okay, if R is a 1 and S is 0, that's this one. I go back to state A. That's my Q value. If S is 1 and it doesn't matter what R is, then I come down here to state D, and Z is equal to a 1. So that's all in this section. Here I'm in state C. There is only one transition, one transition out of here. It's unconditional. So it says if I'm in state C, my next state is A, and this is going to be my new Q value. It's also, I had somewhere up here in some other thing I was looking at, when I put when A, QX is assigned, when I put that right here, QX is assigned, quote, 0, 0, 1, 0, 0, I got error after error after error. So I put it down here, and that got rid of my errors. So if try to remember that if you're seeing, right after saying if you're in state B, you're assigning your QX, that might not be the place to put it. You might get errors there. Okay, so I got all those, and we go to the next one, and so it's finally after I come out of the process that I assign my output its value and my flip-flops their output value. And now I'm going to let Xilinx come up with what's going to be best for Xilinx to come up with JK, T, D, whatever kind of flip-flop it wants to come up with. So the next thing we have to do is come up with our test bench source file, and that's going to be shown here. And then you make sure it's associated to the correct uh, source. In this particular file that I had two source files, so I had to make sure it was assigned or associated with the correct one. Here, um, all my inputs and outputs were added in the test bench. I said it came up with a blank one. It's not really blank. It has everything for your inputs and outputs. It creates signals as is needed. The one thing that I'm hoping it does is create a clock for me, and this time it did. But I think this 10 nanoseconds is too small, so that's one of the things I'm going to do. I'm going to change that to 100 nanoseconds. Here's the rest of it, and it does some more stuff with RNS. I don't know why it has to do this, but it does, and so it does it for you. Here's the rest of the clock. So the two real important things out of here is if you come up with a test bench and you need a clock and Xilinx did not include one for you, then you're definitely going to need this line, constant, clock period, colon, and then give it some, the variable time, colon, equals some value. That can be 10 nanoseconds, it can be 100 nanoseconds, 50 nanoseconds, whatever you want to make it. But this line needs to be in there, so you have to define that clock period. The next thing that you have to do is create this clock process. This gets the clock running, and it runs all the time. I don't have to worry about it. I don't have to come down here in my stimulus process, which is for RNS and any other inputs I have. It just runs by itself all the time. Otherwise, I would have to put in here, clock is equal to 0, wait for so long, clock is equal to 1, wait for so long, and then I would have to also put in my RNS and all that. This is so much easier. Just let the clock run, and it will run. And then in here, I get rid of all this stuff. Everything from, I keep line 90, I keep line 91, and I keep this line 100. And then I take the rest of it out, and that's where I start putting in my values for my inputs in RNS. So what I do, and I'm going to show you how I do this real slowly. I add values one at a time, real slow, and keep running the iSim to see if it's working right, and if it's not, I go back and fix it right then. So some people think that that's a ridiculously slow way of doing it. I think I don't have as many problems with it, and I would end up actually getting done before you would. The other thing I want to say about this clock process, it automatically sets it up to be a 50% duty cycle by taking the clock signal. It said it was 10 nanoseconds. Then here it says clock is assigned to 0, and then wait for that period divided by 2. So if that period was 10 nanoseconds, it's going to wait for 5. And then it's going to make clock equal to 1, and it's going to wait for 5 nanoseconds again. Ends the process, which means it starts it over, because it ends this particular one, starts again, and then it's 0, 5 nanoseconds, and it's 1 for 5 nanoseconds. But there's nothing wrong with saying that clock period is equal, or just say wait for clock period, which is, uh, well, that would be too long. Say that divided by 10, and that would make it 1 uh, nanosecond. And then tell this one to say 9 clock period times 9 divided by 10, and that would make it 10% duty cycle. So you can change these duty cycles all you want. That's up to you. Okay, that's all I have at this point on that presentation. So let's slip over to um, Linux and actually run some of this stuff. Okay, and I'm going to pause this recording for just a minute. Okay, so I had a question about, is there any advantage to doing this uh, math? I guess here is where you're talking about, and down in here. Is there any advantage to doing this? Well, you can say wait for 10 nano or 1 nanosecond, and then here say wait for 9 nanoseconds. As long as that adds up to whatever our clock period is, we can do that. The advantage to this is we're saying I'm going to keep it a 50% duty cycle. So it doesn't matter. You could say 5 nanoseconds and 5 nanoseconds. The advantage comes in when you decide later, okay, here I've got 10 nanoseconds. That's going way too fast. I want it to be 100 nanoseconds. I can put in this 100, and everywhere else it takes care of it. I don't have to worry about it anymore. Up to you. Other than that, uh, I mean, typically you're not going to have a lot of places where you have to change everything, but you'd have to, you'd have to make those changes. Okay, um, let's go in, and what I've done here is I've already done some of this, uh, and that's going to let me finish the rest of this. I don't know when I'm going to get this particular uh, thing done. I'm hoping I get it done pretty soon. The one I was working on was one I had a few years back. I have no idea why it was called Oh Hell at the time, but that's what it was called, was Oh Hell. Now here it's showing that it's using a schematic, but that's definitely not what I was using at the time. So I'm going to close this, and it actually should have come up with the right one. It may have come up with this oh hell, but it's still just showing that schematic. It's not showing the VHDL. Here's the schematic. Now I know that I was just working with this in my office. Open project, it looks like. I don't think that was it. Okay. It's still looking like it's in the wrong place. Okay, projects. This is see, this is going under the wrong place. So it's PC, my profile, personal, and then I'm going under 3132, and I'm going under homework, and it's under one of these. It might be under this. Nope. I'm sorry. I thought it would come right up with it. So uh, I didn't make any notes about where it was. That's DNT, homework circuits. I might have called it Project 6, not thinking about it. Okay, it might actually be, this is where my images were. It's not showing them right now. Um, one. Sorry, I'm gonna have to check all these and see if I can find it. Oop, that was homework 3, and it was circuits. Nope. Let me pause this again. Okay, for some reason it thinks it's already in the project, but it's not letting me see it. The name of that uh, project was Attempt 1. And it won't let me add it. Project. Try add copy of it. It still doesn't let me do it. Okay, it's doing that. Sorry, I am gonna find it. It's in here. Now let's see if I can add it. Still not letting me add it. I'm gonna remove that and see if it'll. Now it says it's empty. Project, add source. Okay, I don't know why this is doing this to me, because it was working in my office just fine. Okay, let me try coming out of this and try going back in. If this doesn't work, then I will have to uh, finish the rest of this presentation and put it out there for you all to see. Add source. It wasn't any of those. It won't let me add it. Project, new source. And if I came up with this and said attempt 1, it should give me an error and say that it's there. It exists. No, I don't want to replace it. Anybody got any ideas? I mean, this is driving me crazy because it says it's there, but it's not letting me do anything with it. It's not showing it. Is it still in there? It's being part of the schematic or whatever? I'm sorry? It says it sees them. It shows the status. It also allows you to specify the design view association. And it acts like it's trying to add them. What it might be doing is since I've got that association with the simulation, see there, it sees it. Open that source. Is that it? There it is. It's just not showing it over here. Okay, but it's showing it under simulation. Okay, I'm going to try this. Here's my behavioral, and it shows all that. It shows the clock period. I want to change that to 100 nanoseconds. It shows all this. I'm going to change all that, or get rid of all that. Save all this. And I'm going to try running this. I don't think it'll work, but I'm going to try it. So it's acting like it's in there, but it doesn't show it to me. So, but I already showed you what the source file should look like. I'm a little surprised that this is showing me these things. It's showing reset is always low. It's showing me a clock that's let's see, that would be 100, 200, 300, 400, 500 nanoseconds. I told it to run at 100 nanosecond period. There's my output Z, Q. Shows I'm always staying at 1. Okay, let's try it this way then. I'll close up ISIM. And what I'll do here is go back and look at actually, I think I can look at this and it's a lot easier to look at. I'll close this for now. If what I want to do is say that if first thing I want to do here is make sure that reset's low for a little bit of time. Um, I made the reset low in that simple. So the first thing I do is say reset is assigned um, 0 semicolon wait for let's see, it's 100 nanosecond period, so I'm going to say wait for 10 nanoseconds, and then I'm going to come down here and say reset equal or is assigned a 1 semicolon. And I'm not going to tell it to wait for any amount of time. I'm just going to save it, and I'm going to try running it and see if at least the reset does what it's supposed to do. And I know this takes a little while to do it this way, but this way I'm making sure I don't have any errors in it as I go along. I'd hate to go in and have tons of errors and then I can't find out where they're at. So this works better for me. Okay, so I see the reason that it's doing this is at the end of my file here. I'm saying wait for 100 nanoseconds. If I don't have that in there, I don't think it would do that. So let's see what happens now. And see, it is going from state A over to C, but that's that one unconditional change, right? Here's one. No, it shows R is equal to 0. R is low, so it goes over to state C. And then this unconditional brings it right back to state A. So that's what we're seeing. It's going to C and A, C and A, and back and forth. Okay, I'll close that up. Yes, I really want to do this. I don't tell it to wait for a certain amount of time. I just tell it to wait for that. And then simulate the behavioral again. Now, I'm hoping that what I see is this little bit of low for 10 nanoseconds and then high for the rest of the time that it runs. All right, let's see what we get. Okay, there's reset. It sees low, and for some reason it never sees it go high again. Okay, it stays in 1. Let's see, wait for what did it have before? Wait for 1,000 nanoseconds. Okay, I'm about to start putting in my R's and S's to see if it takes me to the right states and back. Okay, now it sees that reset low for a little bit of time. It goes high and it stays high. So it made it's still doing the same thing it was doing before. It's going from state A to state C to A to C, A to C, and so on. So the next step is if it goes from A to C and then back to A, the next thing we could do is say R equals 1 and see where it goes from there. I think it should do, if I say just that real quick, R is equal to 1, and I got to make sure that happens during a negative transition on the clock because my attempt 1 uh, VHDL file says that the um, that if the clock and it's low, so clock event and clock is low, so it's the negative edge of the clock. So if I say R equals 1 and make sure that happens on the negative edge of the clock, then here it'll say, okay, R and S are both 0, and then here it says R is equal to 0, and here it will say S is equal to 0, and here it'll be non-conditional again. So it should take quite a bit of action uh, just by this one transition where R equals 1. And here I see 10 nanoseconds. The next negative transition is over here, which is at 100, which is 90 nanoseconds away. But what I really want to do is right here at 50, I want to make R go high, and I want to keep it high for 100 nanoseconds so that it's changing on the positive, but it'll see it during this negative. Okay, so the next thing to do in here is say R is assigned and waits for 10 nanoseconds. R is assigned uh, 1, and then I'm going to wait for 40 nanoseconds. Something's telling me I'm doing this one wrong, but let's see what happens. And then R is assigned a 0 again. Okay. Oops. Okay. Okay. So I see. I knew I was doing something wrong here. I'm still seeing the same thing, and that was because I left R um, high for only 40 nanoseconds. That stopped it there. What I needed to do is uh, have it there, which was 140. Oops. 140 nanoseconds. And then let it stay low for the rest of that time. Okay, so let's see where that takes us. This is why I do it, these test benches very slowly. I don't try to do it all at one time. It's going to mess it up if I do. But now I think I'm going to have it right at least uh, for a whole bunch of stuff. And I'll show you how that fits. Okay, now here we see this is finally working. So I reset, that puts me in state A. That's when R goes high. It stays high during this transition. So because of that transition of the clock, and again, I like to put my reset at the very top. That's just me. And then I like to put the clock right under that. And then my inputs, and then my output. Now, right before here, I like to have a divider, new divider, and that actually should be right there. And I always make these divider color, I make it black so that it just spreads it out a little bit. Then after Z, I'll put in another new divider, and I'll make it black also. Where does it make it? Right there. So now I see Z all by itself. This is okay. This is my Q outputs, and I can spread that down where I can actually see that this is state 1, this is 2, this is, I mean, it could be A and B, and this is E, D, C, and so on. So I can see these are different states. Or if I like it better this way, I can see what the numbers of those states are. So here it's reset. Here's the clock. It's running all by itself, which is great. I don't have to think about it anymore. This process is taking care of it. Uh, no big deal. Then here, at this part of the clock, it sees that R is a 1. And according to this diagram, if R is a 1, I should be going from state A to state B, and Z should be 0. So here I'm seeing that I go from state A, and right here, where this is, I'm going from state A to state B, and my output Z is still a 0. Here's the next one from being in state B, and I'm in state B, and R is equal to 0 and S is equal to 0. I can see them both here are equal to 0. So R and S both equal to 0 takes me over to state 5 or state E. And if I look at that here, it does take me over to what was state 5, and it does show that Z went high. So that's working right. Here's the next transition. R and S are both low. Z is still high, so let's see what I'm telling it to do here. Here I said R was equal to 0, so I went from state 5 to state 4. Z is equal to 1 in state 4. This is also state D, if that's what you want to call it. So here it's 4. Uh, and this is state 1, and that's the second one too. This is the fifth one 5, the fourth one 4, third one 3. That's how I'm counting them. So here it's 4. Z is still high. That's just what it should be doing. Then here I've got transition on the clock, again a negative transition. R and S are low. So right here, S is low. I should go to state 3 and Z should drop. So I do go to state 3 and Z drops to a 0. Then I go here to 500 nanoseconds, and that actually, it doesn't matter what R and S are. I've gone here and it takes us back to state A. So I'm right back to where I started from. Then it starts over again, mainly because I haven't changed anything else. So here is a good place to change something. So what do I want to change it to? Well, I'm back in state 1. I think that's where I was. At 500 nanoseconds, I'm back at state 1. So after where was I? This is where R changed, and that was at 150 nanoseconds. So here is 350 nanoseconds later. Oops, sorry. 350 nanoseconds later. So I want it to be maybe 400 nanoseconds. I'm sorry. I don't know. It's between 300 and 400. I guess the question I should be asking is, what state do I want it to go to here? Here it's in state 1. Here it's in state 1. I could say that R is equal to 1 again, and then I could say S is equal to 1 and keep it 1. That would work. That would take me a little bit further. I haven't gone through each one of these yet, but I've gone through an awful lot of them. So what I'll do next is just make R equal to 1 and S equal to 1 for the next little bit of time. So let's see. Here I'm in state 1. And that's where it was 0, 150. So right here, I want to wait 400 nanoseconds, and that'll put me right here. So here's my, this is this. So I wait for 400 nanoseconds, and then that's right where I'm at now. And then right here, I think I said I wanted both R to be 1 and S to be 1, so that it would take me to these two. And let's see what happens. So here I'm going to say R is assigned 1, S is assigned 1, and then I'm going to wait for 100 nanoseconds again, which is one whole clock period, and they should go low. Okay, let me close this out. let me save all this, and this is the last one I'm gonna do, and hopefully this is enough for those people that wanted to see how do you do this test bench for some of the things that are coming up in your projects. All right, let's see what happened. Again, it does this all the time, so you might not want to spend too much time changing this around until uh, you're ready to start taking snapshots to add to your report and then to show me. Okay, this, I thought I said to wait. Oh, I did. I told it to wait for 100 nanoseconds, but I forgot uh, to tell them both to go low again. So that's what I should have done. Okay, we'll save that. I'll get ready to start running this. It's ready. Okay, this is the last one we have time for anyhow. And I hope it didn't confuse you too much with this. Uh, that file is in here. It just we can't see it, and I don't know why that is. It may show up in my office again. I don't know. Okay, here we are. We see RNS both going high. Here's reset at the top. It goes low for just a moment to reset our circuit. Take me back to state A. Then we went to state 2. We saw S is equal to 0 here. It took us, okay, that was, took us to state 2. S was equal to 0 and R was equal to 0, so we went to state 5. That's what we're seeing. And Z went high. Then at this point, um, we saw both R and S as, oops, right, R and S is both low. So that should take us to state 4 where Z was high. And that took us to state 4, Z was high. Then here, we have both R and S low. So with S being low, it should take me to 3 and Z being low. So it takes me to 3, Z is low. And then here at 500, S was low, R was low. In fact, it didn't really matter because there was this non-conditional transition back to 1. So we went back to 1. And then at this point, both R and S are high. And here's R is 1. So it takes me this way. Okay. Takes me over to 2. And then S is 1. So it takes me over to 2. That's fine. And then the next transition in 2, Z is 0. And since it still sees, I think it still sees, no, I was in 2. I'm not quite sure why it goes to 5 there. But anyway, that's where it went to. So that's it. I hope that helps get some of this done with doing the this uh, I'm sorry, these I'm sorry, I'm forgetting. I'm still blank. What is that? It's not the state machine. The test bench. I'm sorry, the test bench. Boy, my mind went blank there for a minute. So this was a test bench. That was the test bench. I hope that helps some of the folks get ready for the test bench. If you get a file that comes up and you need a clock and it doesn't show it, you have to have that line in there, and then you have to have things like this in there. Uh, you have to have something like this in there. You have to have something like this in there. So there's a whole lot of little lines in here that need to be in there. And then you also have to have all this in order to make your clock run. Otherwise, you got to do it manually in here, which is no fun at all. All right. I'll stop here. I will see you all on Thursday, and we'll have fun until then. Right? All right. See you all later.